start. So we've marked your midterm. I'll give it back to you at the end of this class. I think it was quite easy. I think you thought that too, most of you. It was very straightforward. Maybe the final won't be quite as straightforward as that. Just to see if you were paying attention.
Will we also have a set of questions for the final? A set of written questions and a subset of those questions?
Yeah, there will be some similarity. Yeah,
16.
Well, we'll see. But similar. Of course, it'll be 3 hours long, and there'll be much more work to do on it. So I'll give you your midterms back, I said at the end of the class. I've decided not to give you solutions to the midterms. I think it would be a better learning experience if you figure out what happened, where you missed marks. And you could do that by looking at the lecture notes, the right section of the notes, the book, talking to the TAs, talking to me, talking to your friends. If your friend got perfect, that would be a useful resource. I think one person got perfect on this exam. And then if you still have a problem, then you can talk to me. But I prefer you talk to the TAs first, but I'm always willing. My door's open to you anytime. Yes?
I thought it would be helpful if we have marks breakdown for the assignments marker or some for assignment markers, because it gets really hard to see where marks were.
Lost?
Some comments where marks break down.
Well, you know how much is assigned to each question, right? So I think, again, the best thing is to talk to the TAs if you have problems deciding why you lost marks in a certain question. But it's, it's broken down by questions and sub-questions. Okay. Any other questions, suggestions, comments? Okay, so today we're going to polish off logic, so to speak. So instead of doing bottom-up, we're going to do top-down. Sometimes we call bottom-up forward chaining, and top-down is backward chaining. You see those terms used. And we'll see that there's a direct isomorphism, a one-to-one correspondence between bottom-up proofs and top-down proofs when they're successful. But that doesn't mean that they're equally efficient. And we'll see that the top-down procedure can be more efficient than the bottom-up procedure, although they always produce the same results. They both sound incomplete. Therefore, they prove all and only the atoms that are logically entailed, that is, semantically entailed by the knowledge base. Okay? So we're going to rely actually on this. We're going to show the isomorphism between the top-down proofs and the bottom-up proofs. And then we're going to rely on the soundness and completeness proofs. I gave you two different completeness proofs for bottom-up proving. We're going to rely on those proofs to prove that top-down is sound and complete. So in other words, there aren't any more theorems to prove, which is a relief for you, probably. So just a very quick review. We've got a lot of material to cover. I may not get through all this in this lecture. But we really want to move on to uncertainty because time is marching on. So just a quick review of what do we mean by logical consequence. We mean that G, so sometimes we say G is a logical consequence of the knowledge base. Sometimes we say that KB entails G. I don't think I've used that word before. But we're talking about logical entailment. Okay? What that means is that G is true in every model. Right? So, since this is finite, we can't do this in first-order logics, but in propositional logics, we can enumerate all the interpretations. We can check to see which ones are models. Then we can check to see which atoms are true in all those models. That's an algorithm for deciding if an atom G is entailed, is true in all models. Right? And the reason why we're only interested in the atoms that are true in all models is when I set up this knowledge base, I probably had an intended interpretation of the world in which everything I say in the knowledge base is true, right? So one of the models of the knowledge base is the intended interpretation. I know which one it is, but the computer doesn't know that. So if it's trying to see if an atom is true in the world we intending to be talking about, me and the computer, then the computer has to check and make sure it's true in all models. If it's true in all models, logically entailed, then it'll be true in the one model that is the intended interpretation. It doesn't know which one that is, right? We've done that before. So here's a another very simple example of that. Suppose I have this knowledge base. It seems to have 3 atoms in it, A, C, and H. And the 3 clauses are H if A, and A if C. Then the question is, what does this knowledge base semantically entail? You know, this is the kind of thing you should be able to do quickly in your head now, right? Exhaustively to check that, we just look at all the interpretations. There are 8 of them, right? I1 down to I8, just counting in binary on truth or falsity of the primitive propositions. And for each of those interpretations, we look at each clause and say, is it true or false? Right? So if A implies H, and A is false and H is false, then that is true. Right? Because the only time when an implication is false, right, Q if P, we know that that's equivalent to Q or not P, right? This is the antecedent, P, and this is the consequent. So Q if P is false, if and only if, looking at this, Q is false and P is true. That's the only case of the 4 cases where an implication is false, right? This should be second nature to you as well. So for each of these implications, for each of these interpretations, we can write down whether it's true or false. So this one is false. They're all true down to here. Here, this is false because H is true, the antecedent and the head. So the antecedent A is true, and the head is false. So the implication is false, okay? So we're just working out the truthity of all the clauses. And by inspection, we notice that there's only one interpretation here and another one here where they're all true. So these are the models. So we just write down by inspection which one of the models are, which one of the interpretations are models and which ones are not. So there are 2 models, right? So then we say, what I want to know is which atoms are true in all models. Well, I just go and look at all the models and see which atoms are true in them. So this atom here, A is true there, it's true there, and it's true, H is true there, and A is true there. So these, A is true in both models, H is true in both models, and that's how I determine what is semantically entailed by the knowledge base. Okay, so this is doing it semantically based on the meaning of the knowledge base. But of course, this algorithm, which I've just given you, requires that if I have n symbols, there are 2 to the n interpretations. I have to look at them all, so it's guaranteed to take an exponential amount of time in the size of the knowledge base, which is the number of atoms, right? So, but that's how we determine that both A and H are entailed, right? That's a semantic notion. But then we say, well, I'd really like to be more efficient than that. So I say, well, I will use this bottom-up proof procedure, which basically just looks at setting the atoms that have to be true. A has to be true in every model, so I can set it to be true, right? It's a way of putting, initially that's putting A in the set of consequences. It has to be true in every model, because in every model, every clause is true, right? So A has to be true, and if A has to be true, and H is true if A is true, then H has to be true. It's logically forced, right? So I'm being more efficient in figuring out what has to be true in every model, and that's all this bottom-up proof procedure is doing. Puts all the atoms that are just by themselves in the knowledge base, they have to be true, put them in. Then put all the ones in that are at the head of a clause where those are the antecedent. and so on and so forth, chaining forward. That's all that bottom-up procedure is doing until no more clauses can be selected, until you're finished, you reach a fixed point. And then we say that there's a bottom-up derivation of G from the knowledge base if and only if G is in C. Okay? So that's a proof theoretic notion. And so for the knowledge base above, if you just trace it, you have to, A is forced in because A is in there with no body in this knowledge base, so it gets put into the set of consequences, and then the next time around, H will get forced in, and the next time around there'll be no clause such that all the atoms in the body are in the set of consequences and the H is not already there. So that you're finished. It stops. So the outer loop of this algorithm only takes linear time in the number of clauses. Okay? So it's much more efficient than the exponential semantic version. But the beauty is that they compute exactly the same thing. Right? And we guaranteed that by this these proofs of soundness, where soundness means it derives only the atoms that logically follow from the knowledge base. It derives those, only those, but it does derive all of them. So the exact set of atoms that's derived from the knowledge base is equal to the set of atoms that is logically entailed by the knowledge base. So you have to separate these words derived and entailed. Okay, derived means a proof theoretic notion. It's through a derivation. Entailment is a semantic notion. It's a truth theoretic notion about what's true in the world, the intended interpretation, or all the models in our case. Okay? So as I say, that's efficient. The outer loop is linear in the number of clauses in the knowledge base. And that's why, so what we've got is a theorem if I have a knowledge base and I can derive using the bottom-up procedure an atom G. That's true if and only if KB entails G, or G logically follows from the knowledge base. Okay? That's the soundness and completeness theorem written in shorthand. So that's all review. Is there any question about that? It's a little confusing when you encounter these syntactic and semantic notions the first time, but I've hammered them pretty hard. So these are your learning goals up to here. This is where you should be able to do all of these things. I won't read them out. You can read. And this proof is important, that the bottom-up proof procedure is sound and complete. You can use the proof by contradiction for completeness, or you can use the direct proof by induction that I gave you, using the induction hypothesis. And to me, that is the more interesting proof, and the direct proof is usually more interesting because it's usually a constructive proof. It gives you much more insight into how it works. In a contradiction, you just get a contradiction, you say, well, the theorem's true, but I don't know why. I couldn't give you more detail than that. So that's all review. Now we're going on top down. And first, we'll look at, as I say, we talk about bottom up. The reason we're thinking about that is you've got a set of facts here at the bottom, and then you produce a set of consequences of those, and then you produce more consequences until eventually you end up with the consequence you're trying to prove. Or sometimes we say that this is forward chaining. So don't get confused if we use these other words instead. And so the idea here is you're going from the facts to the conclusion. You're going forward from the facts or up from the facts. So top down, of course, is also known as backward chaining or back chaining. You'll see that. Going from the conclusion back to the facts. So here is visually, bottom up, you go from knowledge base forward to the conclusions, right? G, a fact is proved if it's in the set of conclusions when you've reached your fixed point at the end of the bottom-up derivation. So if you've got your cards, here's a question for you. When does the bottom-up derivation look at the query G? What influence does the query G on the set of conclusions that you're drawing with the bottom-up derivation? So you could easily check that by looking at the description of the bottom-up procedure and seeing where G occurs in the bottom-up procedure. So many of you don't have your cards, or you don't have a clue or something. So I do see a few yellow cards, which is not quite right. If you look at the procedure, where is it? Right here. I don't see G anywhere in there. G only appears down here, right? The knowledge base, you can logically derive an atom G if and only if G belongs to C, but G doesn't appear in the procedure. So the point is that no matter what you're trying to prove, this bottom-up procedure always does exactly the same thing. It always produces the entire set of consequences of the knowledge base, and then you say, oh, I was trying to prove this. Let me see if it's in there. Okay? It does exactly the same thing no matter what you're trying to prove. Now, in this case, you can get away with this because it's a finite knowledge base. In general, in a logic, there's an infinite number of consequences. You know, like if I say 1 is an integer, and the successor of an integer is an integer, then how many consequences are there? Just with those two facts, there's an infinite number of consequences. The successor of the successor of the successor of 1 is an integer, and so on and so forth. Right? So you can't use that procedure. It'll never halt. You'll never get to ask, is 39 an integer? Because it'll never halt. There's an infinite number of integers, and it will never finish. So that's a key point about the bottom-up procedure, that it makes no difference what you're trying to prove. The answer is never. Okay? There's no influence on what happens. It derives the same set of consequences regardless of the query. And so, that's a hint that maybe we should use the query because we should only prove the things we're interested in, right? You don't want to prove everything about the world. You're only interested in one thing. You should ask, what am I trying to prove? What do I need to know in order to prove that? What do I need to know in order to prove those? What do I need to know in order to prove those? You chain backwards through the rules until you ground out in the facts, or you don't, and you fail. And if you do ground out in the facts and you succeed, you prove the theory. That's the only difference between the bottom-up and the top-down. You take the query in and grind it against the knowledge base to get an answer, yes or no. Okay? So we'll prove it by performing, again, see this notion of backward here and top-down, back chaining, starting at the goal. Okay? So the idea is search backwards for a query, and we use this sort of artificial convention. We introduce a new kind of clause. We've had clauses in the knowledge base, which are the rules that are true. In order to answer a particular query, we'll invent a new clause. We'll call it the answer clause. And in general, queries will be a conjunction of atoms. Right? We've only been proving single atoms, but if you can prove each of the single atoms in a conjunction, you've proved the conjunction. Right? So in general, we're going to be proving conjunctions of this form, A1 and A2 and A3 and up to AM, where each of those are atoms, propositions, positive propositions. Okay? So we'll invent this new clause. If we're trying to prove this query, we'll invent a clause of this form, yes. And this is just a device. You'll see why that's useful in a minute. So we express the query as an answer clause. And this is the basic idea. It's called SLD resolution. And SLD stands for, get me some new pens. Stands for selection, linear, definite. And we'll see what each of these terms mean, why they come to be in SLD resolution. But we just sort of introduce it here as just the name of SLD. How many of you used Prolog? You know all about SLD resolution. That's the Prolog interpreter, okay? With unification. SLD resolution and unification is Prolog, okay? So this is all familiar to you. It's just maybe expressed in a slightly different form. And this is propositional Prolog. We don't even have variables or constants. We'll get to them by the end of the lecture, maybe. So the basic idea, SLD, selection linear definite resolution of an answer clause is, if you've got an answer clause of this form with a bunch of conjuncts, C1 through Ci up to Cm, you resolve it against another clause where Ci is at the head of that clause, and you replace that atom by the body of the clause you've resolved against. Okay? It yields a new clause. Looks longer. But of course, C might be in a clause with no body. I mean, it might just Ci is just true in the database, which you can read as Ci if empty body, right? In which case you'd be just removing Ci because you're replacing it with its body, which is empty. But in general, the clause could get longer when you do that resolution. Okay? So this is a rule of inference. Okay? This is the standard way people in logic like to write their rules of inference. Given two facts, you resolve them together to get a new fact. Okay, so above the line we have the two facts that are true, we know them to be true so far. Below the line with the one we produce as an inference. Okay? So given this answer clause here, and this rule in the database, we resolve a new answer clause of this form. Okay, and we can do exactly the same with bottom up. It's what's called modus ponens, only slightly generalized from, if you've done any logic, you know what modus ponens is. You know, A implies B, and you know A, then B is true, right? That's all modus ponens is, and we've just written it this way. H, if this body, conjunction, and we know the conjunction. These are the set, you could think of these as the set of atoms in the set of consequences C in the algorithm. If those are all true, then this rule is true, then this head must be true. That's like adding H to the set of consequences, right? So you can think of both of these methods of inference as having a rule of inference, and these are the two rules. Okay, SLD resolution compared to generalized modus ponens. So we can actually run this. This is just Prolog again, really. So if I have a query typed to the Prolog interpreter, is A true? Yes or no? Then the way the interpreter would determine the truth of it is to construct an answer clause with yes if the query, and try and reduce that to yes if empty. Okay? So we're trying to resolve away the body of the answer clause, is a way of thinking about it. So to do that, it pattern matches into the set of rules and discovers, oh, to get rid of that, I could use that rule there. Or I could have used that rule, but I have to do something, so I'll take that one. And I will replace A in this rule with its body. Yes, if E and F. And I've colored the atoms that are getting resolved away are colored blue here. So I can resolve away F. And it's just a fact in the database, so I can just delete it because its body is empty. So yes, if E, and then I can resolve away the E with this fact, E. Now I have an empty an answer clause with an empty body. That's called an answer. Okay, and that means your query has been successful, and it's linear. The word linear comes from the fact that this proof is linear. Right? I've gone from this query down to the answer, and there's no branching, and there's no tree or anything else supporting this query. Right? Question? Yeah.
Will the procedure look at them in the other definition way? So I know in Prolog it has to backtrack and look at. So would this procedure?
Yeah, it will. Yeah, that'll come up in roughly the 2 slides ahead. But yeah, there will be some non-determinism. There are 2 kinds of non-determinism here, and we'll see the distinction. But yes, I could have picked the wrong clause. I think if I probably picked this one instead, It also has A at the head, it wouldn't have worked. But we'll see. So here their proof was successful, the derivation succeeded, we got an answer. The answer is yes. So that's the definition. An answer is an answer clause with an empty body. Yes if nothing. And a successful derivation is just a set of answer clauses such that the first one, gamma naught, is the query in the body. And each one is obtained by resolving against the previous one with a clause in the knowledge base. Okay, until eventually you get to an answer if you're successful. That's a successful derivation. But it might block. You might get to a point in that linear replacement of atoms in the body by rules, the body of rules, where there's no rule applicable. There's no knowledge-based rule where you can use it to rewrite an atom. So you're just stuck with this answer clause with a non-empty body. That's a blocking derivation. We think of that as a failure in Prolog, which exactly would cause us to back up. Try again. So this is the algorithm. Just as we wrote the bottom-up algorithm in pseudocode, we'll write this one in pseudocode. Start out, set the answer clause to this form, where the body is this query. Select an atom from the body. Choose a clause in the knowledge base such that the clause has the form QI if body, where QI was in the body of the answer clause. And replace that QI by the body of this rule that you selected from the knowledge base. Okay? So here are the two non-determinisms, your two choices. You have to say which atom am I going to choose in the body? I just said QI. I didn't say which, was it the first one, the second one, the last one? So that's a choice. We call that a selection choice. And that's where the word select comes from here. This is selecting which atom to resolve against when you're moving down. Okay? But this is the real non-determinism here, which may fail. Okay, you have to choose a clause. There may be more than one clause which would be appropriate, given that you've chosen the atom to resolve against. There may be more than one clause with that QI as head, and you may have to try all of them in order to succeed. And so you just keep doing that until AC is an answer, and eventually you'll fail if no clause with QI is ahead. This is a blocking derivation. So if you get to a point where there's no clause with QI in its head, you're stuck. You've got to fail back. And you fail back to the last choice point, the last choose you made here. Okay? You don't have to fail back to the selections because you've got to succeed on all the atoms in the body. So it doesn't matter what order you do them in, except for efficiency. It may be more efficient to choose one order rather than another, but they've all got to eventually be resolved away. So this selection is what's called a don't care non-determinism versus this, which is a don't know non-determinism. We don't know what the right thing to do is, so we blindly guess. Here, it doesn't matter what order we do them in, so we don't care. Okay, so we literally call those non-determinisms. Select is any choice will work. That's a don't care non-determinism versus choose, which is truly non-deterministic. You must pick the right one. If we had an oracle, it would tell us which one to choose. If we don't have an oracle, then we'll have to just try them blindly and fail if we get into a dead end. Okay? So in that same example, we could have a failing SLD derivation. So we chose the same rule, but now we chose to resolve F with this rule here, F if K, because there are two rules with F at the head, this one and this one. I chose that one this time. So then I rewrite the F as K, and I rewrite the E as empty because it's a fact. So yes if K, but there are no rules that whose head is K. So this is a blocking derivation on the same query with the same knowledge base. So then I would have to fail back, and I would fail back to a previous choice point, not a selection point, but a choice point, which would be perhaps where I chose to resolve away the F using this rule rather than this rule here. And Prolog, in fact, will always check the rules with no body first, actually, when it's doing a choose. So it's smarter, because that way you're getting closer to the goal. The idea is to shrink the body to no atoms, right? So it's best to always choose the rule with the least number of atoms in the body, and the least you can get is 0. So always try and use your facts first before you use rules with something in their body. That's Prolog's rule, and it's pretty smart. And so here's the neat trick. We don't have to prove that SLD resolution is sound and complete, because we can rely on our proofs for bottom-up resolution by showing there's a one-to-one correspondence between the bottom-up and top-down proofs, right? So in this same knowledge base here, right, suppose we're trying to prove A if B and F, and F if G and H, and so on and so forth, down to this answer. We've proved A is true that way. The way to prove it bottom up would be to say, okay, this H is a fact in the database, so that'll be in C. And then G is a fact in the database, so that'll be in C. So you can see as we move back up the chain of derivations in the top down, we're producing the bottom up derivation. We're collecting all the atoms that must be true, which is what the bottom up derivation does, right? So we just make, and these can only get bigger because it's expanding monotonically as we're proving more atoms. And you can see there's a direct correspondence. This corresponds to that, this corresponds to that, this corresponds to that, and so on. So you can convince yourself that the two algorithms, for this case, that is, for finite propositional definite clauses, these two methods of resolution, one bottom up, the other top down, are exactly one-to-one. They prove exactly the same theory. So we can actually extend this theorem now to say that KB top down derives G if and only if, right? If and only, you know what this means. If and only if, shorthand. So now we've got, you can derive G top down from the knowledge base if and only if you can derive G bottom up from the knowledge base, if and only if G is entailed by the knowledge base, or it logically follows from the knowledge base. Okay? So that's kind of pretty. And in fact, it's incredibly useful. And I showed that this was more efficient than this, and now it's generally true that this is more efficient than this. Right? Because this, the bottom up, produces all possible consequences. It proves everything that's true in all possible worlds. This one only proves that G is true in all possible worlds. So it's much more focused. And that's why Prolog is a top-down interpreter rather than a bottom-up interpreter. Yeah?
Because you can top-down also do the same thing, show all the consequences from the knowledge base?
What it would have to do, you'd have to check for each atom in the knowledge base, you'd have to see if you can derive it top-down. Okay? You'd have to actually determine what are all the atoms in the knowledge base, and then I'd have to prove that each one is true. Right? So for G, I'd have to put in A, B, C, D if they were all the atoms. I'd have to check them each separately. Okay? But usually you're only interested in a small number of consequences of the knowledge base. You're not interested in everything that it proves. If you're interested in everything, you'd probably be better off using bottom-up, because that actually shares some structure and does it more efficiently for all atoms. You'd actually find if you tried to prove everything top-down, you'd be more efficient proving everything bottom-up. But it's not usually the case you're interested in everything that's true. Okay, so that's this statement. Is top-down procedure sound and complete? Yes, there's a one-to-one correspondence between top-down and bottom-up proofs. They derive exactly the same atoms if the SLD resolution picks the successful derivations. Well, we have to see how we organize that search. So this, once again, search, okay? As we've done for every other topic in this course, we're coming back to search. It's inherent in AI. And this is all about logic programming, which is what Prolog is an example of logic programming. So here's an example of a search graph for top-down proofs. For this query, A and D, with this knowledge base, this Prolog program here, this is the space, the search space for successful derivations, right? And if you come down this way, where I replaced A by A, F, B, and C, and so on, I block here. There's no way to resolve away J, because there's no rule with J at the head. So that blocks, this blocks, this blocks, this blocks. But eventually, I back up and find that there is a successful derivation. So there's a proof of A and D for this knowledge base. And if I fail again, when I produce a successful proof in Prolog, it essentially simulates a failure to see if there are any other proofs. Sometimes you're interested in all proofs. So then I could simulate a failure here and go back and search back down there. So what kind of search is SLD resolution? It's fairly simple. Depth first search, just our old friend, right? Failing resolutions are paths where the search has to backtrack. So here's an interesting question. Could you use A star on this search tree? Right? Suppose you wanted to use A star and you wanted to use heuristics, right? Yeah, you can do that. In fact, there have been interpreters for Prolog built using A star. So, as I said, what you're trying to do is to resolve away all the atoms in the answer clause to get them down to 0, right? You can only get rid of one atom at a time. Each atom can only be resolved away by looking it up to be a fact in the database. So the number of atoms in the body is a lower bound on the number of resolutions you've got to perform to find an answer, right? So you need at least that many resolutions, which is the number of steps. We want the shortest proof, typically, right? And that's so that you could use A star with the number of atoms in the answer clause as a heuristic. And it's admissible. Yep, it's admissible because it's a lower bound, as I said. You need at least this many SLD steps to get an answer. And the other reason why this is SLD, I've talked about selection. Selection here means choosing the first atom in the body. Okay? Linear means that the proofs are linear. When I get a successful proof, it's one step after another. It doesn't branch out in any way. And definite means I'm working on definite clauses. These are propositional definite clause logics we're talking about. It doesn't have to be propositional. Prolog is first order, but they're still definite clauses. Okay, so again, inferences search. We've done it for CSPs. We did it for state space search. We did it for planning. Now we're doing it for inference, top-down SLD resolution. We just have to say, what's a state? It's an answer clause, a successor function for all the states that result from resolving against the answer clause with the rules in the body, in the knowledge base. The goal test is the answer clause empty. The solution is the proof, the sequence of SLD resolutions. And you've even got a heuristic function, the number of atoms in the query clause. Okay? So that's nice. We tied it all up in a package. The next step beyond propositional definite clauses is what's called Datalog. It's a subset of Prolog. So, we've got Prolog here. We've got Datalog here. And we've got propositional definite clause logic here. And we've got full first order logic out here, also known as FOL to its spans, and so on, right? And there's a whole bunch of other logics out there. Second order logics, modal logics, you name it. But so the difference between this and this is that we now have variables and terms, we'll see. We've gone from pure propositions to essentially relations. We've got relation, or we'll call them predicates here. And when you go to full Prolog, you get function symbols. But these are all definite clauses. They're still definite clauses. They all still have this form P if A1 and A2 and so on. This is a definite clause. So we kept definite clauses all the way through here. Once we get to there, then we get, we get full negation, we get disjunction, we get all the quantifiers, and we get function symbols from Prolog. So this is just showing how we expand the set of logics by adding new features to the logic as we get bigger. Okay, so Datalog is big in the database community, and it was a way of formalizing what they were doing in databases. And it's the same thing we got when we went from propositions to relations, okay, where we now want to talk about individuals in the world. So if you were talking about an electrical system, this is an example from the book, which you can read up on. We might be talking about various switches and circuit breakers and wires and so on and so forth. If you could only use propositions, you'd have to say things like up S2, up S3, okay, circuit breaker 1, and so on. But the W1 here has no connection to the W1 there, right? These are just individual atomic propositions. They have no structure. There's no way of relating this expression to this expression. And so we'd like to be able to say things like this. There are individuals called switches, and they can be up or down. Circuit breakers can be okay or not. Wires can be live. Wires can be connected to each other, and so on and so forth. And now this W1 is the same W1 as that one. This is a constant, and this is a constant. And they're the same constant. Okay? If something has the same name, it's the same thing. So this is now, say, there's an extension of PDCL, predicate definite clause, propositional definite clause logic, to include variables and relationships between and among variables. And so now we can write rules like this with variables in. A wire is live if it is a wire, and it's connected to something else, W1, which is also a wire, and wire 1 is live. So this is sort of the transitivity of liveness. If two wires are connected and one's hot, the other one's going to be hot, and you shouldn't touch it. Yeah?
I just have a question about the difference between Prolog and Datalog. So what's a function symbol in this case? I thought a function symbol would be something like wire or...
No, these are predicate symbols. Okay? Function symbol in Prolog, if you ever wrote a list in Prolog, you used function symbols to express the embeddedness of a list. If I talk about the successor of a number, the successor of 0 and so on, that's a function symbol. We don't have function symbols, so I'm not going to talk about them here. But so this is just a simple version of Prolog. In general, you'd see function symbols inside terms. They would be, so these are predicates or stand for relationships, and a function symbol would be inside. It would be one of the arguments. A function symbol applied to a variable or a term would be inside the argument of a predicate. Okay? So now we can ask all sorts of things, like you could ask our interpreter, which wires are connected to W1, right? Your database would have a set of assertions about which wires are connected to which wires. And I could say, tell me all the wires that are connected to W1. So now we've got standard relational database theory. We have a set of assertions or tuples about individuals in the world, and we can query it, and we can do database joins and unions and projections and all the stuff that you did in, 304 or whatever the database course is, right? So this is just trivia falls out of all that. We've now got databases. So here's the syntax of Datalog. It just extends the syntax of PDCL. We have variables, and we typically write them with uppercase letters, because that's the way Prolog does it. We have constants, which start with lowercase or digits. We have terms. So a term is either a variable or a constant. And now a predicate symbol is a symbol that starts with a lowercase letter. So it's easy to confuse terms and predicate symbols because they have the same syntax. But it's where they appear in the formula that will tell you the difference, okay? So now we talk about atoms. Before we had atoms, which are just propositions. They're either true or false. Now an atom is a symbol of the form P, which is like a proposition by itself, or a predicate symbol applied to arguments. It's the same semantics. This will either be true or false. But now I can apply a predicate symbol to terms, and a term is either a variable or a constant. Okay? And the only other thing you need to know is definite clauses. Is say, as before, a definite clause is either an atom, that's a fact, a head with no body, or it's of the form head if B1 up to Bm, where these are atoms, and an atom is one of these things. So that's it. That's Datalog, entire syntax. So now we can write rules like this. It's starting to look familiar. We can write recursive rules. There's no law against it. We could say x is in z if x is in y and y is a part of z, which is kind of nice. It's called the transitive closure of part of, if you know any relational algebra. But it's saying the obvious thing. If I've got a set of nested boxes and I want to know if the box in the middle is in the box on the outside, see if you can find a chain of boxes. This is in that, that's in that, and that's in that. And this recursive rule is all you have to say in order to prove that's true. In the knowledge base is just a set of these definite clauses, an unordered set of definite clauses. So we still need to talk about semantics. The semantics of Datalog can get a little tricky. We're not going to do it in any detail. Done in the book, but we're going to... It's obvious. I mean, at some level it's intuitively obvious, but the technical details can be tricky. But it's basically the same idea. We're connecting things in the language with things in the world. That's the basic idea of semantics, right? So you're going to have a correspondence between terms and individuals and between predicate symbols and relationships. Right? So in the language, you'd have statements like this fact, this part of fact, this rule for in of, and so on. That's a Prolog program or a Datalog program. But the way we think about that in our head is we assign semantics to the meaning of the language, and we say this symbol, Alan, stands for this person in the world. This room, 1, 2, 3, stands for this room, and so on and so forth. Okay? So that's the important idea of semantics, and say we won't go into formal semantics, but it's covered in these sections in the book, and that's up to you. Okay, so we're going to stop now, and I'm going to give you your midterms back, and I think the easiest way to do that might be to spread them out on one of these front desks. And if you could try and keep them in alphabetical order.